Okay, I have a few things to say. The first one is about your assignment. You may wonder, where's the solution, right? So you can have your solution probably on Tuesday, in the next week. I'm sorry, this is our TA. Let me just answer it. 여보세요? 아니요. 나를 위해서 딱 한 번만. 한 번만. Okay, sorry about that. So the thing is that there's some changes in numbers in the textbook. So I found out that your problems are slightly different from mine. So my solution is based on my book. And so it's not going to be very useful just to give you the solution that I have right now. And by the way, you do know that there's a typo, right? In question 6.5, part D. So you don't have to worry about it. You're not going to grade it. So one of those r squared must be different. And that different r squared is our subject today. And you probably want to know where is the next assignment, right? So I just checked the textbook again, and I found out that it is okay to give you these questions as the next assignment. So let's just make it official. Is it homework 5? No, homework 9? And you have 1 week to do, okay? Due by next Wednesday. It's very simple, very simple. Okay, so the lecture note today is day 19. So yesterday we did section 6.3. Today I want to do section 6.4. So what is the interpretation of the SCR? It's a typical size of your prediction error, right? So SCR is small here, SCR is large here. Basically, we have the same definition. For a simple regression, K was 1, right? So in that case, SCR was SSR divided by n minus 2. So 1 for single x, another 1 for the constant, right? So we have minus 2. So here the k is the number of independent variables, x's in your regression. So we take the square root of SSR divided by the sample size minus k, the number of x's, minus 1 for the constant. So basically it's the same, it has the same interpretation. So R squared is a ratio of ESS and TSS, or it's 1 minus ratio of SSR and TSS. So there's no changes, right? We have the same definition. And like before, R squared is a number between 0 and 1. It is because even in a multiple regression, we have this identity. So far, there's no difference whatsoever. And larger R squares means that the regression explains lots of variations in the dependent variable. So R squared being 0.6 means 60% of the variations in dependent variable is explained by those k number of independent variables, okay? Or simply by the regression. So far, everything is really good. But when k is more than 1, there's always a problem in R squared. So now if, as you increase k, it means that you simply add more independent variables. Okay? If you increase k, if r squared increases only sometimes, not always, it's not a problem at all. The problem is it goes up all the time. That's the source of the problem. It never goes down. So let's compare two cases. When k is small and when k is bigger. Okay? So let's think about this. If you have a model with 1k, one independent variable, then the error can be written as this, right? And SSR, when k is equal to 1, is written as, so when you increase your k or add one more independent variable, you may have a different SSR, right? Because your prediction will be different. This is the prediction part. The prediction will be different. It means that your residual, the prediction error, will be different. So if you square it and sum them up, then the sum, the SSR, may be different. Okay? Now the claim is, if you increase k, SSR only goes down. It can be equal, but it never goes up. Now let's think about this. R squared is 1 minus SSR divided by TSS. And TSS, simply use your data point and the sample mean of y. Imagine that you add one more axis. Do you change anything in TSS? Take a look at this. Where the k enters. It enters on yi hat, right? It does not change yi. It does not change y bar. The TSS stays the same. Now in the R squared, TSS remains the same. SSR goes down. So R squared needs to go up. So that's the argument here. In case so that's the definition of the R squared. When k is equal to 1 and 2, there's no change in 1. There's no change in TSS. The SSR is decreasing, okay? So you subtract a smaller number from 1. So R squared must increase. So that's this claim. Now I have to explain two things. One is that why this is a problem. Why we care. The second one is why SSR only goes down. So why SSR only goes down as you increase the number of independent variables. Suppose that yi is some kind of dish, food you want to make, soup. You want to make a soup for dinner, okay? Suppose the yi is the kind of quality of soup you want, okay? So that's your goal. I'd like to make my soup as good as someone's, things like that. X1 and X2 are the ingredients, okay? So what do you need for a soup? So say that onion is very important. So X1 is onion, so you have one thing, and garlic is X2. So in this case, you say that this is like, I don't know, water. So you only have onion to make your soup. So this is the quality of the soup you can make, and this is your goal. Okay, the difference is kind of, I don't know, prediction error, disappointment, whatever. So that's the gap when you have onion. This is the gap when you have onion and garlic. Okay, so which one is smaller? Now this problem is actually, how can I say, slightly more sophisticated than my example. But let me just try to give you some intuition. So my claim is that when you have onion and garlic, then you can always do better than when you only have an onion. Do you know why? Because you always have a freedom not to use your garlic. And then you are in the same situation, right? So the thing is that it is extremely easy to be just as good as this. Just never use your garlic. Now, if you have some skill and use your garlic in a good way, then you can only improve. It never goes bad. Okay? So some of you may ask, what if I make a mistake? Put too much garlic. Okay? So the key point in this exercise is this U I hat is a solution of your minimization problem. So the minimization means that you're going to serve the best possible dish you can ever make. So we kind of rule out all this making a mistake, some funny decision type. It never happened, at least in SSR. It can happen, but when you get an SSR, it means that you did whatever you can do. You did your best. Okay? When you do your best, have garlic in addition to onions, makes you better off. Never the other way. Does it make sense? I don't know. So, is it okay if I claim that this is always true? Having a smaller SSR means that you will do better if, in both cases, you do your best. So this is your best dishes if you have only X1, and this is your best dish when you have X1 and X2. Then the best dish under this must be better than. Does it make sense? Okay then. That's why R squared only goes up. So why this is a problem? In many cases, it is not a problem at all. It becomes a problem only when somebody tries to do something stupid. Okay? And many people are actually very stupid. So many people make this mistake. So when you take an econometrics or statistics, there is a tendency that the goal of the regression is to improve the R squared, things like that. So somehow people get that idea. First of all, it's very wrong. Second of all, it is wrong because you can always improve your R squared simply by adding more x's. Okay? Simply because of it, improving R squared cannot be a goal of anything because it's extremely easy. Just add more x's. So you shouldn't do that. Okay? So if you have that kind of idea, just drop it today. And some people actually try to manipulate their regression by putting more x's, although it has no meaning. Okay? So that's very dangerous. So we don't want to do that. So because of that thing, sometimes people just make that kind of a tendency, although that's not very wise. Or sometimes people try to fool others. We like to have something else that is kind of robust. And let's see what happens if somebody increase k. Have more independent variable. Then SSR goes down, right? TSS stays the same. What happens to this? So this becomes smaller. That's in the denominator. The thing goes up. So unlike R squared, there is this, what can I say? The second term that goes to the other way and hopefully cancel the effect. So the good thing is that if you increase k, R squared only goes up, but there's no guarantee. For the adjusted R squared, we do not know until we actually do it. So in that sense, it's better, robust. So let me make a few comments about this adjusted R squared. The first claim is between these two measures of fit, we know that our adjusted R squared is always smaller than the R squared. Can you tell me why? So this is the only difference, right? So why the adjusted R squared is smaller? And typically, k is bigger than 1 because you have x's. Because is it bigger than 1 or less than 1? So this is bigger than that. So it's bigger than 1, right? So when you subtract a number from 1, you know, there's no changes in this ratio. So you multiply a number by something bigger than 1, and then you subtract. So that's why the adjusted R squared is smaller. Actually, a funny thing happened previously. I asked my students to do some kind of project. I forgot. Maybe a homework exercise, something like that. One person submitted a table, and the adjusted R squared was bigger than the actual R squared, very consistently. So you know that something really went wrong. Okay? So when you do the calculation, you can use this fact at least to make sure that you don't make any mistakes. So far it's good. But the second comment about the adjusted R squared is kind of tricky. So it says that the adjusted R squared can be negative. And that's kind of embarrassing. What's the meaning of having minus 4% of variation explained by the regression? So that's one of the disadvantages of the adjusted R squared. And this is why. So let's say that, you know, it's 1 minus this quantity times this quantity. About this A and B, so this is A and this is B. We know that B is between 0 and 1 all the time. For the R squared, it stays between 0 and 1 so nicely because it was just 1 minus B. So 1 minus a number between 0 and 1 makes R squared, again, between 0 and 1, which is very nice, right? Because it's supposed to be some percentage of variation. Now, problem with the adjusted R squared is we multiply another number which is bigger than 1 in front of B. So it really depends, right? Suppose that this is bigger somehow than compared to B, and you can have a situation where the product is bigger than 1. Okay? So in a very unlikely situations, suppose B is close to 1, 0.99, and A is 1.02, things like that. The product can be bigger than 1, and we have this embarrassing moment. So to conclude, adjusted R squared is a good thing. It at least tells us something, but it can be bad. First, because there's no guarantee that you have a positive number. The second is actually worse. R squared has a very nice interpretation. Adjusted R squared has no interpretation whatsoever. When you interpret this, when you multiply this number, all the interpretation we know just disappear. So the only thing we can have is it's going to be close to R squared without some manipulation, and it is a number that is not easily fooled. So maybe it's safe to report this number too. So the convention is sometimes people report two, both of them. R squared is this, adjusted R squared is this. And from the adjusted R squared, what you want to check is whether or not this person is doing something foolish, is throwing more x's, simply to increase the R squared. Okay? That's what you check. If you want to report just one, I actually prefer to report the R squared, not the adjusted R squared, because just knowing adjusted R squared does not provide any interpretation. Just doesn't mean much, right? Okay, so why don't you just try that? I actually don't know the answer, exact answer. It really depends on your data, your model, and many other things, right? But let's see. So in this exercise, you don't have to do it. Just let me save some time. So I'm going to use the idea of simulation, generating data in R. And I just want to know whether throwing more independent variable that is not related to Y can increase the R squared. Okay? So perhaps we can check. Oh, by the way, because he asked in Korean. So the question is, so I just said that if you increase your x, add more x's, useless x's, R squared only goes up. And his question was, is it really true? Because it doesn't sound intuitive. So what I suggest is to check it in R. Okay? Let me just say that, and the sample size is 100. And let's generate our first independent variable, x1, okay? Maybe from normal distribution. And let's generate the errors in this way. And finally, let's generate our y. Now, do you get the idea? So this is our intercept, and this is our slope. Okay? And this is my x, this is my error. So in my case, I actually know the true value of betas. Beta 1, the true value is 0.2. So that's a benefit of using this fake data set. Okay? So this is how the data look like. So we run the regression and put it in the summary. Now what is the R squared in this regression? So I regress y on x1. And x1 actually determines y because it was a part of the model. So what's the R squared? This guy, right? What does it mean? 2% of variation is explained. And by the way, this is the adjusted R squared. Some of you asked me before when to use this, the second quantity, and that's this guy. Okay, so R squared is about 0.2. Now, let me generate another independent variable that is useless. Useless in the sense that it does not help to understand y. Okay? So when I generate y, I use my constant, which is not a data, and I use my x1 and the error. Okay? So x1 is useful to understand y, but let me generate something that is not that useful. So if I say my x2 is simply another random variable, then can I claim that my x2 does not necessarily help me to understand the variations in y? Because it is not used to generate the y, right? So there's no relationship whatsoever between y and x2. They're purely random. Now, let me add this x2 in my regression. And let's examine the R squared. So that's there's improvement, but not a lot. Okay, so previously the r squared was, this is when k is equal to 1, k is equal to 2. What is the r squared right now? Point. And before, what is the r squared? Point 224. So it goes up, although very slightly. What happened to the adjusted r squared? So the adjusted r squared actually went down, right? So x2 is really useless to predict y, but r squared goes up a little bit, not too much. So suppose that this person, kind of still foolish, wants an r squared even higher, okay? And then he wants to add more. So if this person is foolish but kind of persistent, he may try another variable like x3. So in this x3, let me just say that I have 0.5 plus another random variable. Again, this is still useless to predict y because it has no relationship between y. And my x4 has another random variable from uniform. I have x5. Why not have x6? And then run the regression with all these additional random variables. So I have a case where k is equal to 6. Again, throwing a lot of useless independent variables. Now the r squared goes up. Now the thing is that so far, so the r squared becomes kind of double, and anything can happen to the adjusted r squared. So the it's not as dramatic as I wanted. I wanted something even more dramatic, but it still has some point. Okay? So if you increase the number of independent variables and make your model more complicated, the r squared still goes up. It does not mean that you have a better regression model. Okay? Still, the only thing that matters is just x1. Everything else is just garbages. In that case, it's better to make your model simple. Keep it simple, then it's something that's preferable. I'm not sure whether that addressed the question. But let's move on. So the next topic we want to do is in day 20, reading guide. What was the first assumption in the regression? X and U are uncorrelated. Now you have many x's. So all the x's you have must be uncorrelated. What is the second assumption? The data must be random. What's the third assumption? So large outliers unlikely. So basically it requires that the force moment exists. Tail should be thin. So we basically have the same assumption. When you have more than one axis, there's a force assumption. It says no perfect multi So that's the new assumption. Okay, so let's discuss. this new thing. Because otherwise, we are kind of familiar with all these three things. Right? I still don't know how to teach this topic. It's a tricky one. So the thing is that this thing about multicollinearity was really a big topic many years ago. Now it's not a big topic anymore because we have something even more important. So what I like about this textbook is that it has some kind of attitude, some opinion, personal opinion. Sometimes it can be very biased, but it is strong. So I like it. So the attitude in this in our textbook is for the imperfect multicollinearity, which simply means that the x's have strong correlation. The correlation between x1 and x2 can be strong. Okay? Like 30 years ago, it was a big thing. It was a big concern. So people say that we shouldn't have a large correlation in x's. Even now, sometimes when I make my students present, sometimes I hear such comments. I don't know where it come from. But I think that for this matter, I think our textbook is kind of correct. So the textbook says, with imperfect multicollinearity, you don't worry about it. Okay? Again, imperfect multicollinearity means that your x's, maybe two of them, are highly correlated. Is it a problem? Maybe, but it's okay. So as the textbook says, from now on, just don't worry about it, okay? Just drop the concern. Now, what is the perfect multicollinearity? It means that two x's are perfectly correlated. Means that one x is just, how can I say, disguised form of the other x. The example is, if you multiply 2 in x1, you have x2. So the linear correlation is in some sense perfect. Okay? That's actually a problem. And the attitude of our textbook is just correct it. Okay? Okay, so I'm going to give you an example of a perfect multicollinearity. This is indeed a problem because if there is a perfect multicollinearity, that violates one of the regression assumptions, right? So we cannot run a regression. So that's a problem. And this is an example of a perfect multicollinearity. We actually know this example already. So can you open your R? Let's do it together. And read this data set. Can you do it? So in this data set, we have this female dummy, right? So female gets 1 and male gets 0. Do you remember this question where I asked you to make a male dummy? So how do you make a male dummy? Can you make it? Why don't you make it? Now, run a regression of wages on female. Try it. So you know how to interpret this coefficient, right? Now run a regression of wages on male. So we basically change the baseline group, right? In the second regression, the female is the baseline, and this is the average female wages, and this is the difference between male and female. In this example, the male is the baseline, so this is the average wages of male, and this is the difference between female and male, okay? Now the thing is, what if somebody wants to be smarter and use male and female at the same time? So why don't you run it? So suppose that you can easily think it over and say that why not just use both male dummy and female dummy. Now we have a problem in a sense that the regression is incomplete. There's no coefficient for the female variable. And this is an example of the perfect multicollinearity. If you think about it, it's kind of stupid regression, isn't it? So that's the attitude of the textbook. When you violate this force condition, no perfect multicollinearity, you simply fix it. Can you tell me why we have this problem? So we have an intercept, a male variable, male dummy, and female dummy. So what caused this trouble? So if you add two variables, it's going to be one everywhere, right? But one was the first variable, the constant. So that's why I said it's perfectly linearly correlated. So linear sum of some variables, if that exactly replicate another variable, that's an example of a perfect multicollinearity. Is it clear? Is it confusing? Okay, but anyway, think about it. So this is not allowed. You cannot have constant male dummy and female dummy. Okay, that's a violation of the condition number 4. This is allowed. You have constant and male dummy. That's okay. So this is how you fix your problem. This is allowed. You can have a constant and one dummy value. Okay? And of course, what is important is the interpretation of the coefficient. Another thing that is allowed is this. Because we are not allowed to have constant male and female, one thing we can drop is the constant. So this is okay. Okay? So -1 means do not use the constant. Now let me give you a quiz. Now suppose that you like to run a regression of GDP on something, okay, interest rate or whatever, and suppose that you have a quarterly data. You have 4 quarters, okay, and you know every quarter has the kind of its own thing. The weather is different. Sometimes, like 4th quarter, we have a lot of holidays, so factories close down. People don't go to work. In the 2nd quarter, there is summer vacation. So usually consumption goes up, things like that. The quarters are very different. So what people do is to make quarter dummies. The 1st quarter dummy to 4th quarter dummy. So in that case, you can have 4 dummies, right? Now, imagine that you run a regression of, so this is the 1st quarter dummy and whatsoever. Now, does it work? What's the problem with this regression? It's a violation of one of the conditions because there is a perfect multicollinearity. Why? Because if you add all quarter dummies, what do you get? You get 1s everywhere, right? So there's a problem And the textbook says, if there's a problem, just correct it. So how do you correct it? So one idea is drop one of dummies, and that become your baseline quarter. Okay? And everything is compared against that quarter. The second option is drop your constant. Okay? So that's how you fix it. Okay, so it's impressive that we finish everything that I have to finish. By the way, in day 20 reading guide, there is another example. I want you to read it carefully because I may ask it in the next quiz. Okay? So if I ask it and you don't know how to solve it, then that's really a problem. Okay? So read it. Now let me make a few comments about this imperfect multicollinearity. Again, it simply means that you have axis, and it is not perfectly collinear, but simply the covariance between is high. Maybe it's better to use the correlation coefficient. So what it means is that your x2 looks like x1. Okay? It's not perfectly looks like x1, but it's kind of close. Is it a problem? Again, the textbook says this is just one attitude, one opinion. And this opinion is, it's not a problem, just move on, okay? And I think that that's sometimes dangerous, but usually it's better than just worry about this too much, because that's not, maybe that's not the right thing to do. So in economics, the high correlation between axes are very common. So if you care about this too much, then it'll be a problem. So that's one thing. The second one is this high correlation between x does not violate any assumption. Okay? So why do you care? All four assumptions can be still satisfied. So if you run a regression, you can still trust the outcome. Okay? There's no problem whatsoever. The cost, though, is if x is highly correlated, then maybe you can imagine that even if you drop x2, it's not going to change much, right? Because x2 is already very close to x1. So that's kind of a tricky issue, though. So when you keep both of them, so if that's the case, and if you can safely drop one of them, then maybe it's not a bad idea to drop it. If you keep them both, again, it does not violate anything. So you can trust your regression. The cost is it increased the standard error of both x1 and x2. Then what happens to the t-value? It goes down. So it's harder to claim that your independent variable is significant. Okay? So there's a chance that you have insignificant independent variable. So that's the consequence. But again, why is it a problem? I actually think that it's better not to claim unnecessarily that somebody find a significant independent variable in something, because usually that's more costly. If there's really nothing there, but you somehow try very hard to get a t-value bigger than 2 and claim that you find something, I think that's actually a worse than do not find that effect. So still, I kind of go with the textbook and want to say that don't worry about a simple multicollinearity, okay? Because of this. Do you have any questions so far? If not, so let's call your day, and I'll see you in the next week. And there is a assignment, so Don't forget about it. Okay, see you.